physical science time. We're going to talk about fluids today. So write this down. Fluids. Define fluid for me, please.
The flow of liquids.
Okay, you almost had it. I'm going to say
The flow of electrons. Whatever.
We're going to start with this. These two words are related. Fluid comes from the Latin word, which means to flow. So
Then technically,
please, let me just, I will ask you a question when I want to hear your answer. So what does it mean for something to flow?
it's fluids.
Yeah, it can move past each other, right? So if we have water, which is a fluid, right? In fact, when in medicine or in daily usage, if someone says you need to drink more fluids, they probably specifically mean what?
Water.
Probably water. They might include things like juice, but that's most of the water. So they probably mean water. In the physical sciences, not medicine. Please, be silent. In the physical sciences, as opposed to medicine, we consider fluids anything that flows. So let's call it this. Fluids are any substance that can flow. Real briefly, we're going to brainstorm some of them. What are some substances that can flow?
Soda.
Well, let's try not to be that specific.
Water, milk, juice.
Yeah, so in general,
Liquids.
though, liquids and gases. Here we go.
What about molten metal?
What is that?
Plasma. Liquid.
Yeah, molten metal is a liquid.
Oh.
In fact, sometimes we even consider things like granular material, like maybe sand or salt or iron filings. We consider that to flow sometimes. But for this, we're going to specify that fluids are
How's
liquids.
gases?
Because gases can flow. So, for instance, if you, it's hard to see because you can't, most gases are invisible. But you might, if we have like a gas that smells, like for instance perfume, like if we had perfume, we would notice the flow of perfume. If I had perfume and I sprayed it up here, eventually you would all smell it because the gas flows. Does that kind of make sense? And we call, please don't do it. We're not going to do it right now. And even if we could, you can't smell it on the video. And even if you could, I can't smell it anyway. Doesn't matter because we're not doing that demonstration. I'm just telling you that that's one way we can tell that gases flow. There are other ways, but that's one example of how we can tell gases flow. So, any substance that can flow is considered a liquid or gas. We're going to talk about.
This may sound a little stupid, but if
No.
like you say most gases are invisible and like flow in the air, but like gasoline, is that a difference or is it like an actual gas?
I would say that gasoline being called gas by, like normal people, especially in America, is really kind of like etymological or a vocabulary error. Like it's not really a gas, right? So when we say gas in the physical sciences, we mean something that behaves as the state of matter gas. When we say gas in our daily life, we probably mean gasoline, which as you know is a liquid. Please be silent. I'm trying to find it out. Well, you raise your hand and ask me the question, okay? But so gasoline, gas in that case is an abbreviation of gasoline, which is a different separate compound.
Okay.
They might have the same root, but I don't actually know. Josh, what's the question?
It was just, I was thinking, because
Okay.
you said you like live in a gas bubble, there's gas around you. I was like, if we could see gas, and it was like a certain color that we couldn't see, but if we could see it.
Really, that's actually an excellent point because no. So some gas. Listen to me, please. That's a really good point, Josh, because actually, as I said, and you're right, we do live in a gas, right? The medium that human beings exist in is a gas, the atmosphere, air. And does our atmosphere, does the air we live in have a color? Can we see it?
It's clear.
You might think it doesn't, but if you look off in the distance, do it right now. Go look out the window. I'm probably never going to tell you to do this.
It gets
but-
foggy. Like
Yeah,
it's
so
like-
I wouldn't say foggy, but you can tell that those buttes that are over there they appear bluer than they would if we were right next to them, right? Like they're probably about the same color as the nearer buttes. In fact, I know they are. But as we look farther away, they seem bluer, right? And that's because one of the gases that makes up our atmosphere, oxygen, has a color. It's just that we only notice the color when we're seeing through quite a lot of it, right? That's the same reason the sky is blue, because we're seeing through quite a lot of oxygen
And
when
then
we look at
it
the
flies
sky.
off the ocean.
Nope, that's not true.
Whatever.
That's a misconception. The reason the sky is blue is because oxygen itself is blue. It's the same question as like asking Why is your shirt black? It's just the color my shirt is, right? The sky is blue because that's the color of oxygen. Yes.
What color would the sky be if theoretically we didn't have oxygen?
I think nitrogen
Black.
I think nitrogen is completely clear, and so we wouldn't be able to see through. It would just be we'd see the black of outer space. I don't actually know. So don't.
That would be weird.
But I think, please. And the reason I think that is because mostly things are colored because of unbonded pairs of electrons, and nitrogen doesn't have any unbonded pairs. That's not really what this class is about, but it is kind of interesting. Wait,
What about propane?
what color is it?
No, like, is it a gas?
Yes, propane is a gas.
But then why is it whenever you get your propane tank?
We're actually going to talk about that later.
You
if
can shake it and it's like.
Yeah, we're gonna talk about it later if you give me some time. So we're gonna talk about these 3 principles first, okay? So let's write these things down. Archimedes principle. So write Archimedes principle. We're gonna
Archimedes.
define it and kind of give an example. Archimedes principle. We're gonna talk about Pascal's principle. Please. And we're gonna talk about Bernoulli's principle. As we talk about these 3 things, we're going to talk about some other stuff that you're going to, they are vocab words, and so you're going to have them defined already, but we're going to talk about them. And then after that, we're going to talk about what we call the gas laws. So first, we're going to talk about these 3 things, okay? When you have those written down, let's start by defining Archimedes' principle. So there's the story, this is mythology, this is not probably actual history, but the story is that Archimedes, what we would have called a philosopher in ancient Greece, because there wasn't really, people didn't have the tools they needed to do real science, which is that, collect observations, record data, formulate conclusions that are strict based on that. And so they kind of did mostly thought experiments. We might even consider Archimedes a scientist because he actually, at least one case, at least the myth goes, he did an actual physical experiment to test this thing. And so his idea was, what happens when something is submerged in water? What happens to the water that it goes into, right? Because it seems like, you have a brick or whatever, and it takes up a certain amount of space. It has a certain, please be quiet. It has a certain amount of volume, and if you drop it in the ocean, why doesn't the ocean change, right? How is the volume of this brick plus the volume of the ocean not different? And the myth goes that as he was thinking about this, he went to take a bath, and he got in the bath, and obviously the water in the bath raised. By how much, do you guess?
By the amount of
By the exact volume that his body was taking up, right? And so the myth is that he then shouted the word eureka and ran naked down the streets because he had figured out his little problem, right? And so that's like I said, it's apocryphal, it's a myth, but it does demonstrate that the Archimedes principle, to boil it down, tells us that the volume of an object in water is the same as the water it displaces. The volume of an object, let's not say water, let's say submerged.
Sorry.
Raise your hand. The volume of an object submerged in a fluid displaces the same amount of volume of that fluid. If we have a rock with a volume of 15 cubic centimeters and we put it in water, how much will the level of the water rise? By 15 cubic centimeters, right? That's Archimedes' principle. Your question, Wade?
Nothing.
Okay. Please remember to raise your hand in the future, okay? That's generally the case if you'll just let me speak. So you raise your hand in the future when you have a question. What makes this kind of interesting is that if the mass of that object is less than the mass of the water it displaces, a force is exerted on it, and we call this buoyancy. So let's write that down. Buoyancy. You might have heard of, for instance, a buoy, just this word, right? You might have heard of the word buoyancy. But what this is a force exerted. A force exerted on an object due to the fluid it displaces.
So,
Please raise your hand if you have a question. Yes, wait.
so with an iceberg, seeing how it's pretty much more of it's underwater than what it's showing. So whenever it's doing that, is only half of its more than half of its volume in the ocean.
Yeah, more than half of it would be with
Well, sorry,
and that's
I didn't
because
understand.
because the buoyancy gets greater, the lower the mass of this object compared to the volume of water is displaced. And so what would have a very high buoyancy? Something that weighs very little for its size, right? And we'll get to this in a second, but there's a special word for something's mass compared to its volume.
Wait,
Density. Yeah, it's density. And so if it has a very low density, there's more buoyancy exerted on it. What's something that has a very low density?
With paper.
Even lower. Let's go even lower than that. Even
gas.
lower. Yeah, a gas. So like the Earth beach ball in the back, how far down below the water, if we had a tub big enough to hold that, right, and there's the water, how far down into the water would it go? It probably just right on the surface, right? Whereas, even if we had a chunk of, maybe a big crumbled up piece of paper, it would probably submerge a little bit lower because it's more dense than that gas, right? If we had a big old block of iron, it would probably be all the way submerged because the buoyancy would be very little because its density is so large, right? What's the relationship then between buoyancy and density? What kind of proportional?
The less dense it is, the better buoyancy.
So that was what kind of proportionality?
1-to-1.
Inversely. Inversely proportional. Write that down. Buoyancy and density are inversely proportional. Meaning the higher the density, the lower the buoyancy, and vice versa. We call this whole idea, what? Archimedes principle. Remember the guy running naked down the street. Just always think about a guy running naked down the street. Yes, wait.
Why is it that, like, if you were to lay in a big pool of, like, even like the density or something, where it has a lot of salt, why do you have more of a...
Okay, good question. So I think what you're asking is that how come you would have an easier time floating
with more salt?
if there was more salt in the water? What does the salt do probably to these things we've been
Density of the water.
Right, so the water itself would be more dense. And so then your volume that you displace, you would have a greater buoyancy because the mass of that water would be larger, right? So you would float more easily because the water itself is denser. Let's move on to Pascal's principle, unless there are other questions. Thank you for your question. Wait, are there other questions?
So density has like no relation to size, right? Because this beach ball is so much better than so much bigger than a little marble.
This is one of the things that does depend on size because the volume, density is described as the mass divided by the volume, right? And so if that beach ball has a certain volume and we add more and more mass to it, like maybe if we fill it full of sand instead of air, it'll be more dense then, right? And therefore it'll have less buoyancy. So larger objects that weigh less have lower density than small objects that weigh a lot.
Okay.
Because it depends on both mass and volume. Thank you for your question. Others? Pascal's principle is pretty easy. You've recognized this before. This is almost common sense. It is common sense, but here's my toothpaste tube. Nice. This is a side view. We'll say the toothpaste tube is open. And I'm just going to mash this in with a hammer.
Well, then it goes pew!
Right, so I apply pressure over here, right? Some pressure here. What happens?
It shoots out.
Yeah.
It must escape.
This is good.
Somebody-
Right, so the pressure, Pascal's principle is just that the pressure you apply to a fluid is transmitted all throughout the fluid. Pressure applied to a fluid is transmitted throughout a fluid.
So, sorry.
Let's define pressure. You have a pencil? You have a pencil? Take out your pencil, take out your arm,
Okay. It's a hard.
apply some force to the tip of your pencil on your arm. What's it feel like?
Sharp.
Okay?
Kind of.
Now flip it over and apply the same force with the eraser end. Which one do you feel more?
Eraser.
Because it's more of a pinpoint.
So you have a different answer than he does. Which one hurts more? Let's say that.
The pointing end.
The point is, because what's different about it? You applied the same force, and so the force is obviously not different. What is different between the pointy end of your pencil and the eraser end?
There's less.
The pressure is
There's
measured
not
because
enough.
the area. So it depends on two things. Pressure equals force divided by area. Pressure is directly proportional to force, meaning that how can I apply more pressure in relating to force?
You just drag it.
Yeah,
in.
more force, right? More force. And it's inversely proportional to area. So relating to area, how could I apply more pressure? Yes, it's inversely, so a smaller area, right?
Make
Would
it
you
smaller.
rather, if you're lying on the floor and you're going to have someone walk on your back, like you sometimes do if you have a bad back, I don't know. Would you rather have, would you rather have, please be silent and raise your hand if you have a question. Would you rather have someone wearing regular old sneaks or high heels walk on your back?
Regular old
Sneaks.
sneaks.
Yeah, regular old sneaks
Actually,
because the area is smaller and therefore the pressure would be greater with the high heels. Take your question. Okay, that's why snowshoes work, because they have a great big area and so they apply very little pressure to the snow so you don't break through the crust of the snow. Right? Last we're going to talk about Bernoulli's Principle, and this one's, I like this one, I like this one a lot. This one is that, I'm just going to define it first, and then we'll talk about some examples. So Bernoulli's Principle is that as the velocity of a fluid increases, the pressure it exerts decreases. As the velocity of the fluid increases, the pressure it exerts decreases. I love the example of this given on page 488. This is a garden sprayer you could use to spray fertilizer or pesticide or herbicide on your lawn. But basically it's got a kind of like a hose attachment. So this would be your garden hose. I don't know, it's like a gun.
Wait, what?
Here's your garden hose. Water's coming through here, right? And then this is some kind of chemical. I'm going to put pesticide. It doesn't have to be pesticide, but some kind of something that you want to spray. What happens is as the water goes over this, since this fluid is moving, right, the water is moving, it exerts less pressure, and then the pressure that's already existing in this pushes the fluid up into here, and this fluid becomes part of the stream. And so without even having to like shake it out or spray it with a pump, we are able to get this fluid that's inside of this vessel in with the stream of the water because this fluid is moving. It's the same way that a pump, like your little spray cleaner or whatever, spray, you know, like a little spray ball, works on the same principle. The air, which is the fluid, right, liquids and gases, the air, because you're squeezing it, moves across the opening of the pump, and whatever's in the bottle, because of Bernoulli's principle, is pushed out because of the pressure that's inside the container. So for just a moment, while you're squeezing the handle, the pressure in the pump itself is lower than the pressure in the bottle, and that causes the fluid to go up into the pump. Yes, sir. Yes. One last thing before we finish this video. We'll talk about the gas laws another time. But we talked about this last year, but write down the word viscosity. It's one of your vocab words. Viscosity.
The ability for water to flow.
Say it. Yeah, how it flows. How, specifically what it flows.
Fluids, how fast?
How fast it flows.
Oh.
High viscosity means it's going to flow how?
Very well.
Nope, it's the other way around. High viscosity means it's going to, yeah. So we define it this way. A viscosity is a fluid's resistance to flow. The higher the viscosity, the more it resists flow. So what has a high viscosity then? Give me an example. What?
Sandpaper.
Paint? Sandpaper's not a fluid. Paint does though.
Oh, whatever.
What else?
Syrup.
Syrup has a high
Honey.
viscosity.
Molasses.
Honey, molasses. What has a low viscosity?
Water.
Oil.
You think it would have
Like
a
any-
lot?
like
the
a lot of
fluid in your joints.
Yes, synovial fluid, because remember we talked about that in coefficient of friction. Yeah.
And then being all over the floor and just sliding
You
everywhere.
said that if it.
Viscosity-
The larger the viscosity,
Viscosity-
the more internal friction.
Viscosity and lubrication are not necessarily directly related, but you're right. Viscosity is how much internal friction that liquid has. The more internal friction, the more viscosity. Generally, the stronger the chemical bonds between the atoms that make up that fluid, the higher the viscosity. Gasoline has a very, very low viscosity,
Because it's
an even lower one than water. One way
Why
we can
isn't
think,
the gas?
one way that we can think about viscosity is how will this interact with the surface? So something like blood.
I can't shoot.
Here we're gonna have three surfaces. What is blood gonna look like if we drop a drop of blood on a surface?
Little A to B little
Flat.
circles.
So it's gonna a little lump.
Domes.
Water, if we drop water on a surface, will the lump be?
Slow out.
Yeah, it'll flow out more, right? It'll still have a little dome like that. Whereas something like nail polish remover or alcohol or gasoline will just be completely flat because it has very little viscosity. The higher the viscosity, the more domed up this will be.
So-
If we had a little drop of honey, what would that be? It'd almost be like a little bead, right? It'd almost have, instead of being a dome, it'd almost be a little sphere. Yes.
So is that the reason why whenever Roman filled up his water bottle to the brim, it looked like there was a little hill over
Yeah,
top?
because of the viscosity of the water. Do you have questions about viscosity?
No.
Do you have questions about Bernoulli's principle? Bye-bye, marker.
No.
Do you have questions about Pascal's principle?
No.
This boy?